Welcome everyone to this month's Dr. Data Science. And we have our Director of Data Science, Stephen Hillian, who is going to run this. Um, and so, Stephen, can you, next slide, please?
There you go. Sorry,
Yes.
I'm out in the wilds of Holland right now, so my connection is a little slow, but hopefully you'll see the slides.
Cool. Yeah, no worries. Thank you. I want to remind everyone that Dr. Data Science is a recurring webinar we run for our customer, and it's like third Wednesday at 9 a.m. Pacific or 12 p.m. EST. And as you see, next session will be March 18, and we are posting the recording of our sessions on YouTube as soon as we can, but it will be out there in 4 to 5 days. Sometime it takes 1 week, and I will paste the YouTube playlist link in chat in a while. In this session, if you have any questions you want to ask, please post them in Q&A, because in chat it becomes really messy and hard to follow. So please post those questions in Q&A section. Over to you, Stephen.
Great, thanks, Ninad. I'm going to be joined in the session by Nora Husseini. You remember last month I was saying that who is Dr. Data Science? Dr. Data Science sort of represents the sum brain power of the TIBCO data science team. And so Nora is in the London section of the TIBCO data science team. And so she's going to be talking with me about text featurization. Another reminder from last time is that we sort of split up the session into a little nugget of information, stuff that should be well known, but sometimes isn't, which we call information gain, and then we'll have our features session. Last time, we were talking about how do you optimize K? How do you pick which value of K to use in K-means? And then we had a featured session with Nico Rode on deep learning and where it does and doesn't apply. This month, we're going to have a quick info gain on categorical variables, how to deal with those in models that need numerical input. And then our features session with Nora is about text featurization, and we're calling that a vector is worth 1,000 words. Okay, let's get into the info gain. So the question here is, right, what do I do with categorical variables? So why is this even a question? Well, for many model types, you need numerical inputs. You need some sort of numerical or continuous input. And so as an illustration of this, as you think of sort of the classic diagram of like a linear regression, you know, you might have a linear relationship between, in this case, we were doing a study on how parking tickets are related to various factors, including the number of businesses within a particular area. And so it makes sense to talk about, as the number of businesses in a neighborhood go up, the number of parking tickets go up as well. But what's the, like, suppose you were looking at something like zip code, right? What would be the corresponding statement, right? As the zip code goes up, it doesn't really make sense. Now, having said that, right, sometimes categorical variables can be used as they are, like in a decision tree, for example. You can say, is something low or high? Is it red, green, blue, whatever it is. But we want to talk about when we really do need to have numerical variables. So take a data set like this. You've got numerical variables like account balance, where we're trying to predict, say, something like credit rating. But what do you do with a column like purpose here, loan purpose, when it's not a number, but, you know, a purpose like card or auto loan or whatever it might be, or with payment status, which is a number but has no intrinsic order or meaning, or something like zip code or postal code, which has thousands potentially of values. Well, the most well-known method is what's called dummy encoding or one-hot encoding, I think is the more common term. And what you do is you essentially pivot that up into a bunch of binary variables. So for that purpose example, right, we had auto or card or personal small business. You make each of those a column and just say 1 or 0. So it's kind of converting it into a kind of a number, like a Boolean. Now, the problem with this, right, is, well, I think there's a couple of problems. One is that, you know, if you have a column like zip code, that can produce like a really, really wide data set with like thousands of binary columns, which is really unwieldy. I also think that one-hot encoding can be really unintuitive, right? As if you're doing something like a regression, what does it mean to say that, you know, your credit rating goes up the more the loan gets personal, you know, or the more it's kind of auto-y? What does this variable sort of really mean? I mean, it has some sort of intuitive meaning, but as a number, I think it's sort of a little bit weird. So there are other methods that are worth thinking about besides one-hot encoding. And again, the purpose of Infogain is not really to go into these in any great detail, but there is one I wanted to focus on. There are others. Ordinal encoding, right? If there is an intrinsic order, then just convert it into a number, like, you know, good, excellent, bad, or something like that. Feature hashing, binary encoding, a different type of vector methods similar to one-hot. Target or weight of evidence are useful when you have a target variable, a dependent variable. So I want to briefly mention target encoding. It's something that we've been using here at TIBCO quite a lot. It's now encoded within our, if you excuse the pun, it's now embedded within our data science platform. Impact encoding is essentially, just to simplify a little bit, it's substituting each categorical variable, each categorical level with the mean of the dependent variable, right? So in this example that I'm showing you, we're trying to predict housing price or Airbnb price or something like that, I think was the data set. And if you're trying to predict the price, you can take into account numerical variables like the number of bathrooms. But for zip code, what do? Well, a pretty good place to start, right, is what is the mean or median or mean value of the price of the property for that particular zip code. That's a good place to start modeling, is just to take the mean from that particular region. The thing you want to really avoid with impact encoding or target encoding is overfitting, because, right, I mean, if you had like really tons of small levels or small categories, then you could essentially encode the output variable completely, and that would be bad for overfitting. So the trick there is really to use sampling and cross-validation. Don't use the same data for doing the impact encoding, the impact modeling that you use for training your final model. Think of it as a submodel and use different training sets to do with that. But we think it's a really powerful technique. We included it in our AutoML capability. So we would recommend taking a look at that and other encoding methods besides one-hot encoding. All right, that's the Infogain for today. We're now going to move on to our featured session. Hey, Nora, are you with me?
Yes, hi, Stephen.
It's great to talk to you. Thanks for joining us. I wanted to start off, if you don't mind, just with a quick review of sort of standard sort of tech. You know, if you've got a bunch of text, how do you, again, it's kind of like in the last section, right? How do you convert that into some sort of numerical input into a model? Let me show you very briefly before we hand over to you, Nora, just a sort of standard technique, right? You've got here some hotel reviews, and I want to convert that into numerical input variables. And what you could do is just say, build a dictionary, right? Build a dictionary of all of the words that are used in your hotel reviews and just count up how frequently they occur. So for example, in this bit of text, you see the word hotel appear a few times. And in fact, over here, there's the number of times that the word hotel occurs, 3, and you can use that as an input into your model. So if you wanted to look at positive reviews, you might look at words like good or excellent or something like that. The problem is that a word like hotel is going to appear a lot, and you kind of want to normalize that out. So there's this thing called TF-IDF, and you can think of sort of, roughly speaking, dividing out by the number of times it occurs overall in the entire collection or corpus of documents. So for example, you see hotel gets a TF-IDF score of 2.69, room occurs a little less frequency, so 3 times it occurs, but it gets a score of 2.92 because that's a little bit more special. At the other end, a word like pool, for example, here we see pool, maybe it occurs a little less, so that only occurs twice, but it gets a higher score. So that's TF-IDF. It's a very common way of featurizing text, but we're going to look at some more advanced methods now. So Nora, over to you, and maybe you can explain some of the things that you've been looking at for featurizing text blocks.
Thank you, Stephen. Let me just take over the share.
Great.
Can you all see my screen?
You bet.
Great. Okay, so this, what I'm going to talk to you today about is something known as word-to-vec. It's a little bit more advanced than the TF-IDF or the one-hot encoding methods that Stephen has mentioned. So the concept came about by a team of researchers at Google. What they did was not really a novel technique in machine learning. We've seen this before, but what they decided to do was use a neural net to train a corpus, so a big text, whether it's something like a novel or news articles. And they took the neural net's weights within the hidden layer. So they didn't actually use the neural net for modeling purposes, but they used the architecture of the neural net to then translate those words into word vectors that they could then put into other types of models. So there's two typical types of neural nets that are discussed. The one is called the continuous bag of words, and the other is called a skipgram. I'm going to talk to you today about how the skipgram works. It's the more popular one. And a little tidbit about Google's Word2Vec. It is a pre-trained model that you can download yourself, but it's quite big. It's 1.5 gig in size. And it was trained on a Google News data set. So it had a unique number of words of 3 million within a context of 100 billion words. And that will become important because what data you use to train your model informs the different word vectors, and I'll show you more about that later. So a well-known phrase, "You shall know a word by the company it keeps," by the professor Firth, is then translated using this neural net so that you can keep the context of the words within the sentences, as opposed to just seeing the words being counted like you were describing before. So within this teeny corpus of 4 sentences here, we have sentences describing weather, but also time. And using the Word2Vec neural nets, you'd be able to understand that there is some kind of relationship between cold and warm and hot and cool, that even though as humans we understand them to be somewhat antonyms, they understand, the neural net would then understand that actually there is some kind of relationship between these words that we can then describe into a vectorized math space.
So it's kind of like understanding context in a way that those other sort of more dumb methods just don't know. Is that the idea? Exactly.
So the whole point is to preserve the context of the words better than just looking at, a simple count of the words within a text.
Yeah.
Right. So just to explain a little bit more about the context of the words and how the skipgram model for Word2Vec works, I thought it would be clearer by showing you how there is this sort of moving window. So the skipgram refers to the word that I've highlighted here in yellow. And what you'd be doing essentially is keeping the words around it and calculating probabilities of that word appearing again within the corpus, right? So that's why it's very important that the context, that the data set that you're using preserves the context, but it's also important to understand that there are a lot of contextual, cultural elements that then get translated into this vector space, because the vector space essentially doesn't really mean anything. Mm. And I think it's best if I show you this through a quick demo. I'm just going to swap over to share through our Team Studio to show you a little bit better the way that this works with a very simple data set. So here I've got a spam data set. This is text messages and whether or not they're categorized as spam or not. And as you know, text speak, there's, people write things kind of funnily. The idea here is to see if the Word2Vec translator can pick that up and then classify things correctly. The n-gram here, I just wanted to put in to show you that our corpus is actually quite small. It's only about 10,000 words. The Google Word2Vec data set was translated on, as I was telling you, 3 million. So it's considerably smaller. But essentially what we're doing is we're creating that vector space and deciding how big we want that vector space to be. So in this case, our operator, we have decided that we want it to be 100 columns. So we've split out our vector space into 100 kind of axes or columns to translate all of that text. So it's reduced down from 10,000 to 100. And the way that it works is, if I show you through the vectorizer, the text is fed into the Word2Vec vectorizer, so you get the full sentences, and each of these sentences split out into the words that are then averaged to give a number that then helps us classify whether it is spam or ham. Let me just jump back again to the
so basically, every word corresponds to kind of like a point in, or not an actual vector.
Yes, every word corresponds to an actual vector in the space, but we define how big that space is meant to be.
And is that pretty typical? You go down to like 100? Is there sort of like a rule of thumb around that?
Not an explicit rule of thumb, but Google's Word2Vec. So for example, Google Word2Vec was from 3 million brought down into 300. So it can be condensed quite considerably, and that's one of the advantages of using it.
Mm-hmm. Mm-hmm.
Let me just continue. So if we then take whatever number of vectors we've used within the Word2Vec space, and then reduce that dimensionally down to 2 or 3D, so something that's humanly intelligible, you can see some relationships that are quite obvious to us as humans, but they're actually being translated by the computer and in this vector space. So the very famous, the very famous king and queen, man and woman. Have you heard of this, Stephen?
No.
No, so this is quite a well-known paradigm that with these vectors, you would be able to deduce by simply adding or subtracting the gender that king and queen are related by gender. So the idea here is the lines are almost sort of parallel between those two different, there's almost like a space that you can separate between the genders. And it's not just, of course, the genders and nouns, but it's also to other kind of relationships. So verb tense and country capital are equally applicable.
So my understanding of this, right, is through all of these documents or text blocks or whatever, it might like and married the woman, for example, not that marriage has to be between a man and a woman, but, and then also we'll see a sentence like the king married the queen, and understands these occupy sort of the same relationships in space, so to speak.
Yeah, I think, Stephen, the line was cutting, but I think I got the gist of what you're asking. So the idea is, yes, the implicit and cultural depictions of words within text then get translated into the space. Absolutely. Right. And that's a very good point that you're making, because I wanted to show how that actually encourages bias. Google Translate embedded their Word2Vec into the application itself. And Emre Sharbak, a Turkish data scientist and entrepreneur, noticed that when he was translating something from Turkish, which is a gender-neutral language, it was actually implying certain things about gender and about professions that shouldn't have been so explicit, right? So, for example, some of these are quite upsetting as a woman, but also you can see that there was this, because this was trained on the news data set, what gets reported on, the people getting most of the attention as well are inherently implying that most engineers are masculine or doctors are mostly male and such. And that's something that I wanted to highlight, is the bias of whatever data you're using, and also the bias of what we are putting out there on the web then gets translated in these machine learning models. Even though
this is a great illustration of, you know, your model is only as good as your data.
Yes, exactly.
Yeah.
Exactly.
And I can imagine in business context, right? If you're using maybe older data, you might be relying on product reviews, for example, that are no longer relevant. And so, you know, you're drawing the wrong conclusions about people feel about your products, for example.
Exactly. Absolutely. So it is very much about being careful of what data you're inputting and also understanding how that affects the end users. To that point, I wanted to show you that Google did take this on. So it wasn't that, you know, the Word2Vec gender bias was something that they just dismissed. They actually realized that, no, we need to work on making this application better and better for other people. And just as before, you would put in "obir doktor" in Turkish, which means that that person is a doctor. They have now understood that they have to be quite explicit about the fact that there is a gender in English, but that isn't implied in Turkish, and it shouldn't be attached to profession. So I don't want us to be wary of using the technology, but I also want us to be very cautious and to constantly improve upon ourselves. So whether it's things like what data sets we're using to train, and how that affects people further down the line, the people who are then, you know, possibly, say, victims of whatever applications these are then used in.
That's really interesting. It's sort of, not to be too philosophical, right? But it's an example of the dangers of machine learning to, in this case, you know, pick up these biases that are reflected in the data. But it's also an example of how, because these are ultimately, we hope, under human control, the way that we can fix those as well, that we can manipulate the code and the way that we react to the data to counter those biases.
Exactly. Technology, people forget, is not some kind of magical, detached thing that we, engage with in some difficult way. We are creating it. We are the ones who are encoding, and therefore we are also encoding problems that we need to be wary of, and need to be wary of how to address that as well.
Mm-hmm, mm-hmm.
So that is all I have for this session. Are there any questions?
One quick question from me, Nora, or maybe a couple. So if I want to use this, right, how are there open source implementations of this? Does TIBCO, well, I guess you showed us an example of TIBCO doing this, right?
Yes, so you could either just use the concept of training a shallow neural net yourself, depending on the data sensitivity, if it's maybe specific type of text you don't want to be shared, and or that is specific to a domain. So for example, if you're looking at scientific text, you might just want to train everything within, academic speak, for example, is different to spam text messages. So that's one way, but you do, as I mentioned before, Word2Vec is something you can download. So it is sort of like a pre-trained model that you can then download and take those weights and use that in your own applications. That's why.
So I don't have to always provide my own training corpus of documents.
No, you don't. It depends on how big your training corpus is as well, whether you want to do that or not. But again, that's just why I was mentioning that Word2Vec has some implicit funny relationships and funny biases, even though they have a great, because it's trained on such a big data set in comparison to what you might have available for your own purposes.
Cool. And am I right in inferring from what you've shown here that, you really do need to have a reasonably sized data set for training? If you're going to train your own models, if you want to learn from context, right, you really need to have examples. There are a lot of words and they can be used in a lot of different ways. So I can imagine that the corpus needs to be pretty big.
Generally speaking, yes, having a bigger corpus is better, because then you do, as you said, exactly, you get more of the context, and there's a lot of ambiguity in language, right? So the way that people understand certain words may differ, even if people are both native speakers raised in the same place. It is very contextual as in the way that we live it every day. Yeah. But that doesn't mean that that you couldn't use it. It has been shown not to work very well. So for example, I read of some applications, people who are making something for support in Ireland, and then not understanding the way that Irish dialect is, and that making problems for the automated classifiers and such that come through after.
Got it. Hey, one final question for me before we open it up, Ninad, is why were you working on this? Was there a particular project that required this?
Yes, I was working on text featureization with respect to AutoML. So this is part of what you were sharing before about how the categorical variables get encoded. One of the problems we had was trying to understand text, and because it's not a category as in itself, it's a whole other field. So this is why I've gotten to understand Word2Vec.
So this is actually, that thing you showed us before in the data science platform, that's going to be part of the AutoML capabilities, that it will automatically handle text.
Exactly, yes. It will automatically handle text for you and translate that into something that you could, that the models that it generates will be able to use. Yeah.
Yeah.
Cool.
Great.
So yeah, Nura, this session was really cool. So some of the questions users might have is like, according to you, what are the pros and cons of Word2Vec compared to others?
Well, they're not necessarily one or the other. So the TF-IDF that Stephen mentioned before, which is specific to a word, can actually be combined with a word vector. So instead of just averaging, as I showed maybe before, where you had a sentence and then the sentence gets averaged into the vector space, you could use the TF-IDF from that same vector space and use that as a weighting. So then that would help classify the text or whatever task you're doing it for better in your modeling step later on.
Cool. And I guess you already covered some of the part, but what about other languages? You already gave an example of Turkish.
Yes, so exactly. Other languages are quite difficult. I would say if you are looking at languages on their own, it would be best to keep them somewhat separate because there are certain contexts, certain things that are implicit in other languages that might not make sense if you combine them, right? So that doesn't mean that it wouldn't work. So if you had maybe something like hotel reviews that were in English, but also French, it doesn't mean that maybe they wouldn't map to the same sort of space and maybe that the words would translate to the same kind of place if the context is very explicit, regardless of the language. But I personally would suggest that it probably makes more sense to keep things separate because of contextual and cultural and literature reasons.
Yeah, makes sense. Makes sense. Yeah. You already covered some of the part of this question, but how do you combine the vectors for each word so it will represent a sentence?
So generally speaking, it's averaged. If you recall, each of the words gets split out into the vector space that we translate, right? So in the example I showed, it was 100 vectors. And what you do is for a sentence, those words are just added up together, averaged out within that vector space, and then you use it for whatever purposes further on.
Cool. And for example, if you got vectors for 2 words or text, then how do you compare them to see which are like similar or these are dissimilar, that kind of stuff?
You mean how do you compare 2 words and how they're similar or not?
Right.
Yeah, so I think the most common way is because we're talking about vector space, there's usually some kind of distance metric that comes into play. The most famous one is cosine similarity. I'm not going to go into the details of cosine similarity just because we have a few more minutes left. It's quite involved. But I do think that the example I gave of the visualization where sorry to jump ahead. The word relationships are quite nicely translated as well. So you would be looking at most likely words that are quite similar being in the same sort of space, but then also being able to deduce relationships between words and such. The only purpose of this diagram here was to show it in a human intelligible form. So, most people understand king and queen have a gendered relationship.
Okay, cool. Yeah, that's interesting. So I guess that's it for this month.